So this is part two of a two-part workshop. Can I have a show of hands, and you Zoom attendees can raise your hands in the chat. For anybody who attended the intro workshop this past October, I'll give everybody a minute to respond. And Alex will relay the information to me. I'm guessing that not a lot of you, if anybody, attended that. Okay. In that case, we will spend a little bit more time today reviewing what we did in October, just so you can get a feel for where we're at. And then, does anybody have any prior SQL experience or database modeling experience? And we'll give you guys a second to respond. Beginner? Yeah. What's the HAPS online at, Alex?
Looks like we've got two that have.
Okay. All right. Well, just good to know, so I can get a feel for the experience level here. So what we're going to do today is we're going to review the things that we went over in October at the intro workshop, and then we're going to discuss many-to-many relationships. And then we're going to talk about normalization. We'll take a brief detour into ER diagrams, and then we'll write some SQL. And so we have 80 slides to get through, and probably half a semester's worth of material to cram into a 90-minute workshop today. So we're going to have to move quickly, and we'll see what happens. So what did we cover in October? These are the things that we covered in October. We talked about the definitions of database, relational databases, what a relational database system is, modeling a basic database, which we will spend a little bit of time on today because I think it's important to know what you're querying. And then we talked about keys, tables, primary, surrogate, and foreign keys. And then finally, we wrote some SQL together. So let's blow through that. What is a relational database? Well, this is the definition that Wikipedia has. I did not like this definition because it was not clear. So I think I told the group in October that I prefer to learn by doing. So that's what we're going to do. SQL, we defined SQL. It stands for structured query language. And it is the primary way for querying relational databases. It was invented after relational databases were postulated and defined. But nevertheless, it became the industry standard for getting access and modifying data in relational databases. All right. Now, relational model of data is a conceptual framework. So that doesn't mean it's an implementation. There are many products out there that implement relational databases. And see, here is a very non-comprehensive list of them. Most relational databases run on servers, somewhere out in the cloud or on a separate system, but there's no reason that you can't run both the server and the client application on your own computer. Regardless, it still adheres to the server-client model. In most cases, you'll need to start a process on the computer and then use a client app to interact with the database. Here we used MariaDB and IDSQL as the client and server and client rather. So on a server out in the cloud somewhere is running MariaDB, and on our workstation here, I've got IDSQL set up. And we'll get to that in a minute. Now, that's up on my notes here. Then we started to build a relational database. So when you want to build a relational database, you have to have a problem in mind that you want to solve, right? And so we postulated a restaurant, XYZ restaurant, and we started off with a simple use case. We have a need to track customers' names, email addresses, birthdays, and favorite dishes. All right, so the first step is to determine a problem statement. We've done that. Now, my preferred tooling at this stage is pencil and paper. But in order to make this workshop work, we need to use digital tools, right? Because it's on the screen. So once we have a problem statement, the next thing to do is to identify the nouns. So XYZ restaurant is a noun, customers is a noun, names, email addresses, birthdays, and favorite dishes is a noun. But all of these nouns are kind of related to the customer, right? So the customer has a name, customer has an email address, etc. And so we will focus on the customers. Now, we need to keep it simple to start. Complexity is the enemy at this step of the process. So we'll start with a tool that most everyone should be familiar with, a spreadsheet. And then I've already pre-filled the information that we covered in October. So you can see here that we've already set up our customers spreadsheet. And they have a first name, last name, email address, birthday, and favorite dish. Now notice that we have two lead kings here, right? Is this a data entry issue, mistake, or are these different people? Well, let's see about some clues. So Lee King at example.org, and this one has a different email address. They also have different birthdays and favorite dishes, different favorite dishes. So we can reasonably assume that they are different people. Now, I don't know that for sure, but as far as my data is concerned, they are different people. But how do we identify two different Lee Kings? So Lee King and Lee King, say there was another Lee King, right? How would we differentiate those records? Well, our spreadsheet assigns each row a number, right? So we have Lee King number 4 here and Lee King number 7. But what if I do this? Number 4 became number 7 and number 7 became number 6, right? So that's not a good way of keeping track of our individual people. So what we did was we added a unique identifier column, all right? So this is going to be number 2 identifies this noun in all space and time as a separate entity from all other entities. Lee King, the individual. We assume that this is a separate entity, human, right? So number 2, ID 2, represents this particular individual, regardless of whatever else changes in this record. So let's say Amy Stake got married and changed her last name. Well, as long as her identifier remains the same, we know that that's the same Amy Stake. Likewise, maybe a data entry error occurred when somebody was entering her birthday and it was actually March 6th. But we can change that and still know that this is Amy Stake because of this primary identifier. So this is called a primary key. And it is completely necessary for data modeling and RDMSs. Every group of records requires a primary key. It's also called a synthetic key or sometimes a surrogate key because it has nothing to do with any of the information in this record, on this row. So number one is a completely arbitrary identifier, and that's by design. Every table or spreadsheet you create should have a primary key that has nothing to do with any of the information in the table. Synthetic keys are so common in relational databases that most systems have built-in features to set up a column, and we'll get to that later. The most common form this takes is, like I demonstrated here, an auto-incrementing integer. So if we added more records, we'd have records 6, 7, 8, 9, 10, etc. But you can use anything as the primary key. A lot of times they use universally unique identifiers, if you know what those are. There's long strings of characters. Yes.
Is it only a synthetic key once it's a primary key and it has no relation to the data, or are they the same thing, or just another name for it? Primary.
Yeah, so the question was, is it only a synthetic key if it's primary key? Primary keys are only the
Sorry, so is a synthetic key an alias of primary key, or is a synthetic key a primary key that also isn't related to the other parts of the data, like a universally generated ID?
So yeah, so you're asking if I added another column here, right?
So say if you use email as a primary key,
Okay, yeah.
is it not a synthetic key because it is related to the rest of the data?
That's right. That's exactly right. So say he asked if we used email as a primary key. Well, what if the user changes their email?
Mm-hmm.
Then we have no way of tying it back to that particular individual, right?
Mm-hmm.
So that's a good question, actually, because you have to think about your data modeling when you're developing relational databases and expect anything to change, any possibilities.
I think the other part of it too is that you can have more synthetic keys that aren't your primary key throughout the.
Yes, but that's out of the scope for today's discussion.
Right.
You said you can have more synthetic keys that aren't your primary key, and that's completely true. You could have these synthetic keys as you want in this table, but probably you're only going to have one, and it's going to be your primary identifier, primary key. Big questions. All right. So let me see where I'm at here. Now a moment to discuss terminology. So we discussed terminology. I'm going to blaze over this slide because it's not apropos for today, but relational databases are actually conceptualized before spreadsheet technology, if you can believe that. So the database terminology is a lot more arcane than the spreadsheet terminology. I think the spreadsheet terminology is more intuitive than the RDMS. But so what's called a workbook in the spreadsheet world. And a workbook is just the combination of all the spreadsheets that are in that workbook. And so you can imagine 3 or 4 extra ones out here for each spreadsheet. That's called a schema. So workbook equals schema. Whereas a worksheet, the individual sheets in this workbook are called tables in RDMS. So I'm going to refer to this as the customers table, and this is the dishes table, etc. And then here's where the below the table and schema, the database terminology is muddled with the has become muddled with the spreadsheet terminology over the last couple decades. And so you'll hear me use the vernacular row when I mean record, or the vernacular column when I mean attribute. But row is equal to record. So this is a record. This is a record. This is a record. Column attributes. So these are attributes. And finally, cells are called fields. But again, the vernacular has become muddled with the last three terms, so you're gonna hear me use whatever language. All right, so we emphasize that surrogate and synthetic keys should always be arbitrary values. And then we've cleaned up our spreadsheet a little bit, but that's already been done in this example here, so we're gonna move on. Again, attributes, records, primary key, table. All right. Any other questions before we move on? Online, Alex? Okay, good. So let's go back to our spreadsheet. Now, let's say that we want to rename a dish. We want to rename the pizza Super Duper Pizza. Well, I could do a search and replace, but that's not the RDMS way. Furthermore, if I want to add additional information about a dish, like say, keep track of the price, right? Dish price. And then we'll start adding prices. Well, that actually, now we have to change 2 attributes instead of 1, right? So this is not a good way to keep track of it, right? The spreadsheet only, or the tables / spreadsheets only represent 2-dimensional data. And so we will delete this. And so the solution for this is to build a separate sheet, which we did for dishes. So I always add my primary key column first. And you'll notice that I'm naming things consistently across my tables. So ID should be ID. And then we have a name and a price. Why not? Now we need to establish a relationship between those 2 tables. So every time I see pizza in my customers table, I'm going to replace it with the number 1. And I won't belabor your time because I've already done that. Well, I will belabor your time because I use it. Hide
There
these
you go.
cells. There it is. All right. All right. So every time I saw pizza in this table, I knew it was number 1, right? The other table. Chicken, likewise, number 2. And finally, fish, number 3. Now, I can manipulate the data about the dishes independently of my customers, right? And so say we want to change the price of pizza, inflation happened, so we got to raise the price to $8. Boom, done, right? All right.
I would say it also saves you, so that way you're not typing it again. Like,
Yeah,
You have
it
the-
saves, like, this is the correct way to model data. All right,
just is.
all right. So let's flip back to our presentation here. So we have customers. All right. Customers. And dishes are tracked separately. And we have a relationship between the 2 of them. That's the relation in the relational database model. Now, what is this column called? Well, it's called a foreign key. In the customers table, the foreign key to the dishes table is called favorite dish ID. And so elevators, favorite dish is chicken. And we're going to see how to get reports cleanly out of this database when we get to the SQL part. All right. Now it's time to open up our actual database client, which I've connected to a database in the cloud. Can you see the meeting controls in the Zoom, Alex, on my screen?
You shouldn't see it. Be invisible.
Okay, yeah, sorry about that. So I've pre-filled the customers data, as you can see, not the exact same data. Again, Heidi SQL is my client, and XYZ Restaurant is my schema name. And so we're going to just flip through the tabs here to give you a brief tour of this tool. Here is my table customers, and I've entered first name, last name, email, birth date, favorite dish ID, and state. I didn't have state in the example spreadsheet, but I do have it in the customers table and database. And you can see here that the ID column is represented by this gold key right here, which just indicates it's a primary key. And it's number type, integer is what that stands for. And then here we have it set to auto increment. First name, last name, and email are all variable character fields. Birth date is date field, because we have that in our database. And then favorite dish ID, the foreign key always has to match the data type of the table it's representing. So ID is an integer in the dishes table. If foreign favorite dish ID wants to reference that column, it should have the exact same type definition. Now, data types, there's a lot of them. And last October, we went through the basic types of data. Basically, char and varchar and integer and float. So char and varchar are all text fields. I guess text is a text field, obviously. And integer floats are numbers. Date times are self-explanatory. And tiny ints are actually 1 or 0. That's the only valid values for that code. So you can think of those as Boolean, true, false. This is not a comprehensive list, as the slide title denotes. There are many more data types, but these are the ones that we'll be working with in this workshop. And you can see there that they're in the table. The dishes obviously have an integer ID, varchar, and then the price is a float. So a float means that it's a number that can accept decimal points. Integer, no decimal points. All right. So, we're still in last October. Bear with me. We introduced a new branch in our business requirements. We want to track events. And specifically, the names, dates, and times, and the primary contact person for the events. Well, obviously, we need another table called events, right? And so we modeled that table. And here it is. All right. First, we created our ID. Notice the consistency in naming conventions. Very important. We have a varchar field name, and presumably this event will take place at a particular point in time. So we indicated that added that as a column. And finally, we made the assumption that anybody that's organizing an event is already a customer in the customers table. So this is a foreign key field for the customer table. And here's the data. So we flip to the data tab in my database client, and Halloween blowout is organized by whoever customer ID number 5 is, and office party is organized by whoever customer ID number 6 is. Notice that the order doesn't go in date order, right? This one was added after this one. But it has, so you can't count on the order, any order, to be consistent in your RDMS. Likewise, birth dates are all over the place, right? That's to be expected. Everybody, customer that walks in the door gets a record, and they all have different birthdays. So yeah, you can't count on, likewise, customer ID number 5 might have organized the Halloween blowout before customer ID number 6 organized the office party. All right. And so here is our database model at this point. Customers. We can have one customer organize multiple events. So you can see here that the graduation reception and office retreat were organized by the same person, Lee King. So this is a one-to-many relationship. One customer can organize many events, or restating that from the event perspective, many events can be organized by a single customer. Likewise, we have one dish that can be any given customer's favorite dish. So many customers can have the same favorite dish, right? 3 to 3. So both Lee King's and Paige Turner's favorite dish is the fish. So these are called one-to-many relationships. By the way, this is a schema. And what this type of diagram is called is an entity relationship diagram. And we'll see more of these later on. Anyhow, we're getting the phase, this should be phase 2 in your data modeling process, entity relationship diagrams. And there are many tools that help you create them out there, and we'll see a couple later. All right. An example of one out in the wild is this video store rental diagram from ancient times. I just found this on the internet, and it's very small, I'm sorry, but I'll send out the slides to this whole group who registered, and you can peruse this at your leisure. It is actually created by a free tool that put out by Oracle called MySQL Workbench. All right. Any questions? All right. So then we wrote some SQL. So let's write some SQL to get our blood moving. And so we're going to flip over. So we've looked at the tables tab and then the data tab. So the tables tab just gives you the definition of the table. And the data tab shows you all the information in this table. And then we have the query tab, which is actually where you write your SQL. So now this is a very fancy SQL client. In the olden times, we just had the terminal. So you'd see a big black screen with a prompt, and you needed to write SQL. So let's just pull a basic SQL query report. Select star from customers. So the star means all fields or all attributes. Select means I want to see these things, and from means from the customers table. And we'll just hit the play button here. And it shows basically the same thing as I would see in the data tab. Now, I can't guarantee that data will be shown in the same order as the data tab, but it's highly likely. All right, let's do another query to get warmed up. Let's see, we want to see everything from the dishes table. Well, again, select star from dishes. Shows all the data from the dishes table. Now, it's not necessary to put our control words in uppercase. So this will work just as well. Oh, see, my client is helping me out here. It automatically puts it in uppercase when I hit the space. But in case you're using a different client, it's not case sensitive. All right, let's introduce some constraints, shall we? So I wish there was a way to turn that off. So we're gonna go back to our customers. And let's say we want to see only the customers that live in Florida. So where is our constraint keyword? State equals Florida. FL. How the data is represented in our database. And so this shows only the people that live in Florida. Let's add Georgia in. So, or state equals Georgia. All right. So if anybody has any experience in programming languages, this should be very familiar syntax. And we've added the Georgia people too. Let me show you another one. State in parentheses, Florida, Georgia, Alabama. All right. Now I'm omitting an important thing here, which is the SQL version of the period, which is a semicolon. And again, this is standard programming syntax for anybody who's ever programmed in C language before or any derivative languages. But you'll see that in parentheses, a list of states adds the people from Alabama into my query in no particular order. Now, a couple of things about the syntax here. I could have used double quotes for all of these. Notice it changes the coloring though. My client. Oh no, I can't use double quotes. So I'll undo those changes. And it runs. We'll just do one more. We'll take off this clause and put another one on. Let's see, birth date. Is there underscore in between? I don't remember. So let's flip back to our data columns definition, table definition tab. No, there's no underscore. And then is less than or equal to 1959 10-01, let's say, and single quotes. All right, let's see if that works. Okay, it didn't give me an error. It means one of two things. Either my query is malformed or there's no data in the table that matches these criteria. So let's make it a little bit more liberal. Okay, so my query is well formed. And these three people were born between 1975. All right. Questions? All right, let's move on. Oh, sorry, Alex.
Any suggestions on beginner-friendly clients? I'm using dbeaver and MySQL, working my way up to a home DB on SQL developer. Do you have any suggestions on what?
So the question was, any recommendations for beginners regarding clients? I would recommend for Windows users this program I'm using right now, Heidi SQL. I started with it when I was a wee lad in database development, and it's been around forever. If you're on a Mac, I would recommend this other program called SQL Pro, SEQUL Pro. Both are good clients. If you're on Linux, well, come chat with me after because you should know what you're doing. All right. Any other questions, Alex?
That's it for now.
Okay.
And for SQL Pro, did you say SEQL?
Yeah, just the word SQL spelled out fully. Pro.
Thank you.
Okay, let's review some syntax. So the keywords in all of my slides are going to be in yellow. And so this select is a keyword, from is keyword, where is a keyword. The attributes will be in gray. The tables will all be in light blue. And the operators, the mathematical operators, so this is state equals Florida, for example, will be in red. And then finally, the literals will be in light yellow. I don't know what that color is. All right. So now we're going to talk about pushing data in different tables together. So let's see if let's come up with a basic query. I want to see each customer's favorite dish. Okay. So first thing we're going to do is put all of our sections of the query on different lines. That makes things cleaner. SQL doesn't care about line breaks. It'll still run. And then we're going to get rid of this square clause for now. All right, so how you put two tables together. This is really the meat of relational databases. You join them together. All right, so we're going to say join dishes. And now we need to know what the foreign key is in the customers table and what attribute it references in the dishes table. So we're going to use the keyword on customers. Oh, look, my client is helping me out here. Take advantage of that. Favorite dish ID equals dishes dot ID, primary key. So what the foreign key is in the customers table, we're going to join to the primary key on the dishes table. And we're going to just play this query and see what happens. All right. So notice that it includes both the records from the dishes table, or sorry, the customers table and the dishes table. So all the attributes from both tables are included, including the price. And you can see there's redundancy here in our report, right? That's on purpose because we need to represent this data in a two-dimensional report. This is the only way you can represent it in a two-dimensional report. There has to be some redundancy. But in our data model, there's no redundancy here, right? All right. Now, I'm going to narrow down our query so that we're just pulling out the first name, last name, and name of the dish. So in these cases, in this case rather, I've just selected three particular columns: first name, last name, and dish name. Now, you'll notice something confusing in the output here. First name, last name, and then the name, right? So we're going to give that name an alias, which requires use of the as keyword, and then we can call it whatever we want. Dish name. I'm using underscores because I abhor spaces. And now that's a much more clear report. So actually, really, it's the favorite dish name, right? Favorite dish name. I can call it whatever I want. All right. So let me add a new query tab here. And one thing I like about all modern SQL clients is that they allow you to do this kind of thing. You can flip back and forth between multiple queries, which is nice. Let's see who organized which events. So we're going to start with the customers table again. I'm just going to do select star from customers, join events on customers. Well, sorry, it doesn't really matter. ID equals events organizer customer ID. All right, again, this is the foreign key, which references the primary key. And these two, this relationship right here is associative in nature, which means that it can be either direction. It's the same thing. So either foreign key first, primary key, or the other way around. It doesn't make a difference. Let's run this query. And sure enough, you can see here all the information about the customer and all the information about the event. And so we want to limit the columns in this again. Now, notice that when I hit the space button, my client wants to uppercase it. So this is called a reserved word or a keyword. Now, my client is smart enough to know that it's also the name of a client or it's an attribute in one of my tables. So it doesn't, it automatically does some magic in the background. But if I ran this query in a command line, it might fail because it thinks name is a special MySQL word. So what I do with these is I surround them by backticks. And it's not single quotes, it's the character next to the one on the keyboard. But you can do this for every column if you want. It's not necessary, but it is good practice. And we're going to alias that too, because like this name is ambiguous. Now I didn't have to backtick my event name alias, but again, might as well be consistent. All right. All right. Let's go back to our first query. Finally, we want to see these ordered by last name. Essentially. Order by last name. I can put the backticks in or not. And we get them in order of last name. Last name, first name. All right. Are there any questions at this point? Cool. One last thing. Okay. One last thing to demonstrate. Notice that Shay King does not have a favorite dish, or I needed a pizza does not have a favorite dish, although we can guess hers, right? And notice also that I'm going to add the ID to this. Shay King is ID number 24. And she's not included in this query result. Likewise, I needed a pizza is 32. And she's not included. So what this is called is an inner join. And an inner join is only the records that have columns or records in both tables reported. So both customers and dishes. Any customer without a corresponding dish will not be included in this report. If we want to show all of the customers, regardless of whether they have a favorite dish or not, we need to do what's called a left join. And so this is important to get the table that you want to see all the records on the left side. So we want to see all the customers. So we're going to put it on the left. And then only those customers' dishes will also be included. And so we get this output. There's Anita and there's Shay. Excuse me. So by default, all RDMSs perform an inner join if you don't specify the type of join. Now we could definitely explicitly declare the type of join we want, and it would work. But by default, if you don't specify the type of join, it'll assume it's an inner join. All right. And so I've created some pre-diagrams for representing this type of relationship. outer or left joins. Left joins are also called outer joins, but if you try to use that keyword on MySQL at least, it'll throw you an error. So, oh, that's not correct syntax. So I just refer to them as left joins. And then there's the dimming. And then there's the inner join example. And notice that I have a nice Venn diagram down here. Okay. All right. Let's do some aggregate function queries, and then that's where we ended up on our October workshop. So let's say I want to count the number of customers I have. Well, I use this count function, and I see that 26. Or let's say I want to see the total price of all my menu items. I'm going to give it a alias here from dishes, and my total menu cost is $22.50. And finally, one other query type that we want to use, we'll probably be using later in this workshop, is the concat query, which smashes a bunch of text fields together. Okay, so along with whatever literals you want to add. So I'm smashing the first name, then a space, and then the last name together from my customers. And you can see here that it named the column the function name. So I'm going to give it a nice alias as full name. All right. And that is pretty much where we left off in our basic workshop. So before we move on, are there any additional questions? All right, let's move on then. Moving on. We have a third business requirement now. In addition to names, customers, dishes, and events, we need to keep track of orders that those customers place. So our restaurant needs to track orders. Orders can include multiple dishes. Right? So let's model a table now. All right, we're going to have the orders table. Reset the timer here so I can keep on track. All right. What information do we have to have in it? Well, we know we need the ID, our primary key. We know we need the customer that ordered the table. Put the order in, right? That's going to be a foreign key to our customers table. And I should have really named this customers plural ID because I need to keep naming consistent. That's important. All right. We want to know the date and time that the order was placed in order to keep track of that. And then finally, we need to keep track of the dishes. Now, there can be multiple dishes per order, right? So there can be many dishes in one order. How do we model that? All right. Well, we could have multiple attributes, one for each dish. So we have dish 1, dish 2, dish 3. We'll add these columns, attributes to our table, and then fill in the records with the dishes that the customer ordered. But what if the customer wants to order 4 dishes, 18 dishes? This is not a tenable model, right? So we want to have our restaurant make as much money as possible. So that's out. What if we put multiple values in one attribute? So dishes would be a comma separated list, value list. So we can imagine an order with pizza, fish, and fish, right? 2 fish dishes and 1 pizza dish. However, This has many drawbacks and violates normalization rules, which we'll get to in a minute. So that is out too. So what should we do? Well, our business requirement says orders can have multiple or many dishes. Dishes can be part of many orders. So we have a many to many relationship here. Now, how do we model that? So we have orders over here on one side, dishes on the other. And we'll create a third table. It's called a join table. And we'll create our separate relationships. One order to many orders underscore dishes. So, and then one dish to many orders underscore dishes. Now, bear with me. We'll see how this looks on the next slide. I had that slide by accident. Hang on. Oh, I see what I did. Moved it to the wrong location. All right. Legend. All right. All right. So here's what it looks like. Orders, dishes. Order number 1 was placed on February 1st, 2025 by customer ID number 40. He ordered 1 fish platter and a second fish platter. Order number 2 was placed by customer ID number 15 on the same date, a few minutes later. She ordered just 1 dish. So we create a row or record for every dish in the order. So orders ID is a foreign key to the primary key on the orders table. Likewise, dishes ID is a foreign key to the primary key on the dish table. What this allows us to do is assign as many dishes to as many orders as you want. Now, the key word thing to note here is that there are no many-to-many relationships in relational databases. There are only one-to-many relationships. So, and join tables. So if you want to create a many-to-many relationship, right, I should say you need to create a many-to-many relationship. This is how you do it. Create a join table with foreign keys pointing to a primary identifier of the records you want to join together. All right. All right, so this is represented in ER diagrams as shorthand, many to many. So if you see this in an ER diagram, just know that there's a hidden join table here in between these two tables. Why N instead of M? N as in Nancy instead of M as in mother. N can represent any number of records. So it comes from mathematical notation. Likewise, just to show our existing relationship between the orders and customers table here, this is many orders to one customer, right? Each customer can place many orders. Or from the orders perspective, many orders can be assigned to a single customer. All right. I want to pause for a minute here and take a side trip into database normalization rules. Let me reset my timer so I stay on track. First of all, I'll take any questions that y'all have though. Okay. Let's talk about normalization. Normalization is a systematic process of organizing data in a relational database to reduce data redundancy. Okay. Okay. That's a lot of words. What does that mean? It involves decomposing tables into smaller, well-structured tables, defining relationships between them according to specific rules. Specific rules. We're going to discuss 3 levels today of normalization: first, second, and third normal forms. So first normal form states values in each cell should be atomic. The table should have no repeats. And it also postulates that row order should not matter. Dictates. I usually don't postulate, I meant dictate. So in order to have your database in first normal form compliance, you need to adhere to these 2 rules. What do they mean? Well, atomic means 1 value per field. And so when we were dreaming up our hypothetical column with multiple values in that orders table, that is a no-no. So that violates first normal form. Row order should not matter. So what that means is data can be entered in any order as our date times. These keys should be completely arbitrary. There's no other way of saying that. Now, there is one more subtle violation. So those are 2 obvious violations, right? But there's one more subtle violation in our join table. And I meant to have this nicely animated, but I messed up my slides, so that's on me. But notice we have the same dish in order number 1. Yeah, order number 1. So customer ID 40, she ordered 2 of the same dish. Now, we assume that this database is behind a front-end user interface of some sort, like a web app or a point-of-sale terminal behind a checkout counter. How do we know which one to remove from the order? Well, in this example, it doesn't make much of a difference because we're only tracking the relationships in this table. But so we could removing one is as easy or as effective as removing another. But let's say we added a new attribute to this table called preparation reference. And that's what I did accidentally when I all right, prep preference. So order number 1, dish number 3, customer number 40. Let's say that we have a new attribute called preparation preference, and this dish doesn't have a preference. So we might get the usual way that dishes are prepared. However, this fish is the customer ordered well done. So we should cook it a little bit extra, right? Likewise, this customer number 2, has a preference of no sauce on their chicken, etc., etc. All right, so now we have a need to identify each one independently, right? If we remove this dish number 3 from order number 1, it does matter which one we remove. Let me get back to where it was in my slides. The solution for this is a primary key in our join table. Now it's not technically a join table, though. It is actually a first order entity in our database if we include another bit of information. And so that's one rule of thumb that I'd like you to keep in mind. Join tables, many-to-many relationships are often hiding intermediate entities that should have their own information. So we're going to rename this dishes in orders. So it's no longer a join table. It's graduated to an entity table. And notice I'm using standard notation, ER diagram notation in my example here. One to many, many to one. Anyhow, code smells are a term that we use in programming world that say, this smells wrong, something's wrong here, right? And so the first normal form code smells are columns with multiple values or join tables without primary keys. Those are both code smells. Let's talk about second normal form now. No value in a table should depend on only part of a key that can be used to immediately identify a row. Gosh, what does that mean? Well, to demonstrate second normal form, we'll dream up a scenario where we have to keep track of event locations too. Say our restaurant has multiple locations that events can occur. And so that might look something like this. So party time is in the main dining room level 1. Graduation reception is in the main dining room level 2. So restaurant has 2 stories, plus a terrace. So office retreat is on the terrace. Notice that the graduation reception booked the terrace with customer ID number 7. And so the office retreat that's usually on the terrace had to use the main dining room. Whatever. We currently have 3 locations in our restaurant, it looks like. So what if we tried to decided to change the name of this location to something else, right? Maybe main floor or some such. That would require updating multiple records, which is a code smell in relational databases. A single query would suffice to update the name, like search and replace equivalent query. Update query is what that's called, but we don't have time to get into that today. But this is technically a violation of second normal form because there's repeating data. Furthermore, like the dishes table example from earlier, what if we wanted to add more information about each location, such as a price to rent it? So that would require a lot of data duplication, which is a violation of second normal form. So what do? Well, first of all, this is a foreign key field as an aside, so it should really be named with the table name and the column name it references. But how to fix our second normal form? Well, we'll create another table, event locations, and then we'll put all the information about the event locations in that table, and then we will create a one location to many events relationship. Now, since you guys missed the, most of you guys missed the intro workshop, I'm going to model that in our client right now. So I'm going to right click on this and create new table. All right, so we will start with our ID column because that's what we do for every single new table. We won't allow null, that means allow no value, which we don't want for our primary key. And then auto increment, which we do want for our primary key. And then finally, we will set it to right click again and set it to be our primary key. So that's our ID table, our ID column attribute. And then we'll give each location a name. And we have to figure out which kind of text field we want. You can see here that there's a lot of different types of text fields, but we basically, if it's not long paragraphs, we should choose varchar. It makes it queryable. And so I'm going to say the maximum length will be 512 characters per bytes. We don't want to allow null, so we won't check that. And then finally, we'll do a price. And we will do a float. Also, no null values. The default is 0. That's my client doing that. I'm going to say no default value. So we have to put price in. All right. So we have the ID, name, and price of each event location. And then we will save. Huh. Okay. So, yeah, table needs a name. Event. There it is. Locations. And there it is. Now, we'll add some data to it. Hit the plus button here. Now, our database engine software automatically assigns IDs. So we're going to just set that to null, even though technically we're not allowed to in our data definition, but we're going to keep that blank for now. Main floor, and the price to rent it is $500. And then we'll hit the check mark. Notice that it put number 1 in for me. So that's the database engine that added the ID. And then we'll create a second location. All right, you get the idea. Check mark. And automatically assigned ID 2. So now we need to go back to our events table and add another column, which will be a foreign key. To the event locations table. It'll have the same definition, which means not allow null. Never allow null. Actually, when making foreign keys, we need to decide whether we want to require this relationship for each event, right? Do we want to have a location specified for each event? Well, that depends on your work business processes. If you want to reserve more ephemerally before you decide on a location, that's your business decision, right? You can put reservations in without a specific location. But we don't want to allow that. We want to know where the event is happening right from the get-go. So we'll save it as a not null. And then notice here that both of these are 0 because the database engine had to put something in. So we'll just give it actual records. We'll say event location number 2, 1 and 2, and there they are. Yeah. One other reason I like this particular client is that everything is an SQL query that you do in the interface, and it logs it here in the bottom. That's a very nice thing. So you can see here that the update syntax, we're not going to be able to get into today. We updated the events attribute, and we set the event location to 1. For record ID number 1. Okay. So, code smells for second normal form. Lots of repeating data in tables. So we saw that with our dishes, favorite dish ID, favorite dish for customer, and we saw in our event locations. All right, third normal form. Value should not be stored if they can be calculated from another non-key field. So to demonstrate that third normal form, let's say we have for a 50% discount to seniors off of normal menu item prices. So we might want to add a senior price attribute / column to our dishes table, right? Problem with that is somebody could come along and update the price, but not update the senior price, which would violate our business rule. So $12, let's say inflation happens and pizza price goes up to $12, you'd have to update 2 attributes now for each row that you change the price on. And that's a violation of third normal form. So how do we solve that? Well, I don't think we're going to have time to show the queries today, but either within your query or in your front end application code, point of sale machine, web app, etc. And then the smell is that attributes that show the same information, but in a different form. For example, discounts. because that discount is derived from price field. All right. We're going to skip over some stuff. Here's our updated entity relationship diagram. It's a mess, which is why there's tools out there that do this better. The first one is from a tool called DataGrip, and it indicates the foreign key relationships to the primary keys and the reference table. So one customer can have many events, but it's not completely clear which fields reference which primary keys. So we need to look at the table and make sure we're naming things correctly from the get-go to figure out which is a foreign key and which is the primary key that it references. Now, it does list the foreign key, primary key reference on the relationship, which is nice. But this is kind of a messy, and you can imagine if there was like 50 tables in this database, it would become a mess. This is MySQL Workbench. Its style of ER diagramming. It's a little bit more clear, but now you can't see any information about which foreign key field references which primary key field. This is the many side of the relationship, and this is the one side. So you kind of have to figure out intuitively, okay, customer's ID is probably the reference to that customer. This is my favorite diagramming tool. It happens to be free too. Anybody can like go to the website and just punch in an ER diagram, but it's the clearest that I found in my career. It clearly shows the relationships between the foreign keys, the many side, and the one side. So here we see customer's ID references the ID field in the customer's table. Likewise, the ID field in the dishes table, well, one to many, right? You'll notice though that the one side is sometimes represented by a little tick, or it can be a circle. And that just means that that relationship is optional. So customers don't need to have a favorite dish, but if they do, we need to report it in the foreign key field of the dishes or the customer's table. Now, the events should always have a customer that's organizing it. And here it shows that I've modeled the database so that it doesn't require a customer organizer. And so that should be a flag to me to fix my data model, right? I made an error. So that's why I like this style the best. All right, let's write some queries while we still have time. Yes.
Going back to the normalization forms, does the like a higher form also take on all the rules of the other ones?
Yes, I was going to mention that. So what was the question was does a higher form take on the rules of all of the other ones? So
The lower ones, yeah.
Yeah, lower ones. Yes, it does. So they're additive in nature. So you have to achieve third normal form compliance, you have to both be in compliance with both second and first normal forms. Good question. All right. Let's say I want the report. I want a report. I want to see customers' names, order IDs, and dishes that were ordered since January 1st, 2025. All right, let's pull up our favorite entity relationship diagram. So customer names are going to come from the customers table. Order IDs are going to come from the orders table. And finally, the names of dishes, I should have put names of dishes, will come from the dishes table. So we have to write a query that will produce a two-dimensional report with this information in it. One other thing, we can start this query from either, I'm going to use my laser pointer here. So the terminus on this query, the terminating tables, the customers and the dishes, because it goes this way, right? You have to traverse this way, or we could traverse this way. It really doesn't matter where you start the query, but I'm going to start it with the customers table. Okay. So I'm going to switch to my database client now. I'm gonna close. Oh, I don't want to save that. Select. I'm gonna start with just the customer. So I'm gonna say first name, last name from customers. And I'm gonna make sure that works. Notice I have a period on the end there. It's proper grammar. It works. Okay, now we need to connect it to the orders table. So we're going to do a join. Join orders on customers. Oh, you know what? We didn't create a foreign key in the customers table yet. So let's go back and put that in real quick. Oh, we didn't even model our orders table. All right, create new table, orders. Y'all, I messed up. Add name, care. Don't allow null, auto increment. Add customer key. Again, it needs to match the ID definition, the type, data type in the customers table. Well, now number. And we'll set our ID in this table. All right. And let's add some records real quick. Oh, that doesn't exist. And we'll add another record. And one more. Okay. Customer number 23 put in 2 words. And we'll model our dishes join table same way. Add ID. Allow null, no. Auto increment. Make this the primary key. Add. Is orders. Now we need to put 2 foreign keys in. Dish ID. The default value. And orders ID. And technically, if I were going to do this right, I should put dishes ID in because that's the table name. Always important to be consistent. All right. And we'll just fill in a little bit of data in there too. So we won't worry about the primary key. It's 2, order 1. Dish 2, order 1. And dish 2, no, order 2. Finally, we'll put fish in. All right, that's good. All right, now go back to writing our query. Customers, orders, customer ID equals customer ID. Customers. All right. Now, we got this error. Does anybody know why we got this error?
Because you're joining 2 tables that both have a column called ID.
That's correct. He said that we're joining 2 tables that both have a column called ID. So we want to select the ID column from any table. We have to put the table name in. And let's make the Again, this is called a fully qualified name, and we're gonna put it on the right. All right, let's run that again. And sure enough, it runs. So now, which ID are we using in this report? The order ID, and the report just shows the name ID. So we're gonna give it an alias. And that makes it more clear. All right, so let's go back to the presentation. So we're gonna add fully qualified names to all the columns in our table. Or attributes. See, but using both interchangeably. And make sure it runs. All right. So we have this already. All right. So we have the customer names and the order IDs. Now we need the dish names. By the way, fully qualified names and databases consist of a schema name, table name, and attribute name. Now we only have one schema, so we can omit the schema name. All right, and the query ran successfully. So we do have this linkage so far. One customer per many orders. Now we need to add dish information. However, to get to the dishes table from the orders table, we need to traverse through the dishes and orders table or join table. So we'll do that. Join. Dishes in orders. Now, something wrong with that because it should have. Okay. On dishes in orders, order ID equals dishes in orders, dish ID. And we'll select we'll add that to our select. Now I'm gonna make this a little bit cleaner by putting each select on its own line. So we're selecting this information, and we're using these linkages. And sure enough, we get the dishes ID. Now I've missed every one is 2 though. What did I do wrong?
Join the table to itself.
Right. So this should be joined to the orders table, right? The dishes in orders ID equals orders ID. Let's see if that works. All right. That looks better because in order to represent this data in 2-dimensional form, we need to have some redundancy here. So order number 1 has 2 dishes, both fish, and order number 2, I'm sorry, both chicken, and order number 2, this customer has chicken and fish. But what are we doing wrong here? I mean, like, what is this, like, what is the name of this, right? So we have the we have this information now, the dish ID, but we don't want the ID, we want the name. So what do we have to do? Well, we have to do another join. So we'll just put another join in there. And I know we're almost out of time. We're going to join dishes and orders to the dishes table on dishes in orders. That's the foreign key. dishes ID equals dishes ID. And then we're gonna add, now that we have the dishes table in the party, dishes name. See if that works. And sure enough, that works. So 3 chickens and 1 dish. And now we could also add more information from the dishes table now that we joined it to the other tables, like price, right? Price. All right. All right, one other thing, this is getting a little bit verbose here. So we're gonna simplify this query. First of all, we no longer need the dish ID because it's redundant with the name of the dish. So we're gonna just pull that out of there. And then we're gonna add an alias, dish name. In fact, we'll add aliases to all of these columns. Oh, it already has an alias. And then we're going to concatenate using the concat function. And then we're going to put an alias on that. And finally, I'll say customer name. We're going to get rid of the price because that's not required in my business requirements. I want to introduce one last concept to you, and that's called table aliasing. So when you have a bunch of tables that are named long names like dishes and orders, you can actually alias it by putting an alias behind it. So customers will be represented by C in our query. But when we do that, we need to change all of the references to C in our query. Likewise, we'll do DIO. Actually, we'll just do DO. Nope, that's a keyword. DIO. And then again, we will change the all the references to it besides the initial reference in the join. Make sure that runs, and then finally we'll do D for dishes. All right, and that's a lot cleaner. All right. One last thing before I let you all go today. What's missing from this query in our business statement? Anybody online? Okay, I know I've belabored this point, so, and I'm almost keeping you over.
Casey,
Since what?
you were asking about what the error was?
No, I'm asking what's missing.
I have an answer.
Okay.
Semicolon.
Nope.
Maybe
Good
the
guess
order,
though.
order product.
Yes, order since January 1st,
You go where
2025.
statement.
Constraint, right? So we're gonna add that to our query and then we can all get out of here. Now, I didn't add a date time column to our order table, which was omitted. So we're just gonna add that real quick because we want to keep track of that order date, right? And then we need to decide whether we needed to keep track of the date, time, or date time. I always choose the most precise measurement. And then so we're just going to fill in that value. So we'll put this one 2024 and 2023. All right, now we should only have one row that appears in our output. Date time is greater than or equal to 2025 01, 01, 0, 0, 0, 0. Okay, this is how you represent dates, time columns in MySQL. And sure enough, we only have order number 1 shown. He ordered 2 chickens. All right, we're out of time. So I didn't get to, well, I'll show you what I didn't get to. Full bill for order number 2, aggregate queries, and this will all be in the slides if you want to run these things, by the way. Full bill for all orders. And then I didn't think we were going to have time to get to this one. But I expected to have time to get to the prior one, so obviously I need to tune my workshop timing better. But remember the third normal form violation? Well, I was going to demonstrate how to solve that in a query. And basically, it's virtual columns. So discounted price is the sum of the price divided by 5, or times multiplied by 5 rather. As the discounted price. But if you want to run these and build the database, I will include the schema in the materials. And these are additional topics that we didn't get to today, but we're out of time now. So if you want to continue your database learning journey, I would highly recommend this LinkedIn learning video series, which I borrowed a lot of the material from, so you'll be familiar. And that's the link to it. And again, I'll be sending this out. And finally, there's a survey with a QR code attached, and so let me know how I did.